Offshore wind delivers scalable green energy to high-demand population centers around the world. And at the heart of offshore wind is a geotechnical engineer, which ensures installable, safe, and cost-effective foundations through world-class engineering. In the past 2 decades, we've seen a rapid growth of offshore wind, and we now exceed 100 gigawatts capacity installed globally. The industry initially set out in Northern Europe, supported by generous subsidies to enable industry to grow and take form. About 10 years later, around 2015, the industry had really matured, and we saw competitive auctions taking place all over Europe, and that showed that offshore wind was able to deliver renewable energy at competitive prices. And this accelerated the industry and expanded its growth into new regions, and we saw China, we saw the rest of Asia, and we also saw US grow, at least for a while. As an engineer behind the desk, it can be hard to comprehend just how large these turbines have become. Here I've shown the new 18 to 20 megawatt wind turbine class with a 280-meter rotor together with the Eiffel Tower. And to the right, you see the nacelle of a GE 12 megawatt in US a few years ago, and just notice the size of the workers on the ground. Supporting these wind turbines are the foundations, and as engineers, we aim to optimize these to reduce the material and the costs, but always without compromising the safety of the structures. Offshore wind turbines have seen a rapid and continuous growth for decades. A strong driver behind this has been the cost of energy productions. Larger turbines, they simply produce less energy, at less cost per megawatt. Another important driver is the water depth at sites for offshore wind. Larger turbines allow bottom-fixed offshore wind to be cost-effectively used at deeper waters. And today we see jackets and monopiles in the excess of 60 meters of water depths. The growth of the turbine size has been constantly evolving and accelerating. How large the turbines will become in the future is something that we still have to see. Will the growth continue, or will we see a plateau? A similarity is the airplane industry, where we saw the introduction of the Boeing 747 make a plateau, and we didn't see a growth. But we think it continues. And I think the other big question is what role Chinese turbines will play in the future. As you can see on the graph to the right, we now have Gold wind turbines in China leading the race towards bigger turbines. I think most of you are quite familiar with the various foundation concepts used in offshore wind, but here are some of the most classic options. To the left, we have the gravity base, a direct foundation typically used for shallow water. Then we have the pile foundations, which include monopiles and the pile jacket. And next are the concept using suction buckets, including monobuckets, and then the suction bucket jacket. And finally, we have the floating foundations. And this list is not complete. There are many other foundation concepts that are being used out there. Here we see the use of foundation concepts over time. In total, we've seen installation of more than 16,000 offshore wind turbine foundations. And outside China, the number is close to 9,000. Of these, the mostly widely used concept is the monopile foundation. And secondly, we have the pile jackets. Other concepts, such as the suction jacket foundation, we only see that being used limited. And what we also see is that the monopile keeps being the foundation of choice, even as we see larger turbines being deployed at larger, deeper waters. And for developers, the monopile is the most cost-effective and the preferred option for several reasons. It's efficient in the steel usage, it's suitable for mass productions, it's suited for handling and transportation, installation is quick, and it can be used in most soil conditions. Other foundations are typically only introduced when the monopiles cannot be used for one reason or the other. For example, when monopiles they can't be driven, or when noise restrictions prevent impact driving. When we received this invitation to give this keynote, Alistair and we had many thoughts on which topic to address. Over the years, we've worked in detail and in depth with many geotechnical topics. But we decided to tell our stories, which is a rather unique personal journey at the center of the offshore wind industry, spanning the last 2 decades. So here we will give an overview of the design evolution of the monopile, the jacket, the suction bucket jackets, and finally we will give you an outlook of the offshore wind industry. There are many equally important topics from offshore wind that we will not address, and these include site investigation, structural engineering, and installation assessments. So my own journey began in 2005 when I was a newly graduated structural engineer and a keen sailor found a job ad where they looked for engineers to join the offshore wind sector. I ended up joining the company Ørsted, which would later become the global leading developer in offshore wind. I was only one among 3 engineers in the beginning, and we were the green-haired hippie sitting in the corner. If you wanted a career, you needed to build a coal-powered power plant. And by the time I left Ørsted in 2015, we were more than 3,000 working in offshore wind. So being there from the start meant that if you had the ambitions and drive, you could quickly rise the ranks and get a lot of responsibility. And during the time I was in Ørsted, I completed an industrial PhD, and at my defense, I met Alistair in Denmark. As part of my industrial PhD, I came to Oxford, where I worked with Brian Byrne and Guy Holsbury. They had in the past been working on offshore wind turbine foundations, but it was mainly looking at suction casing foundations. I began to look at monopiles, and specifically the response to long-term cyclic loading. It was a new topic at the time, but since there has been a wide range of research undertaken on this specific topic. The work and relations that I got with Oxford University marked the beginning of a strong collaboration between Ørsted and Oxford that would last for decades, also after I left Ørsted. After Oxford and Ørsted, I began to dive into the monitoring data that I could find. The first commercial offshore wind farm to use monopiles was the Hornsea 1 offshore wind farm, which was constructed in Denmark in 2001. From this wind farm, I had access to strain gauge measurements below the soil, SCADA data from the nacelle, back analysis of damping from emergency stop, and finally, I went offshore to measure permanent inclinations. And my conclusions back then were clear. There was a massive room for improving the design. So after completion, I began to push for change in Ørsted. I wanted to ensure that every offshore wind farm being installed at Ørsted had a comprehensive monitoring equipment installed, so that we had a feedback loop that allowed us to learn from the as-built behavior of these structures. Here you see me personally installing equipment at the Hornsea 1 offshore wind farm. Also, I led the development of our internal bespoke software in Ørsted, what we call Optimum, and the intention was really to develop a software that would automate design processes and allow us full control over the applied design methods, and thereby allowing us to optimize the monopile foundations. In 2011, the results of the work were clear, and internally it became a huge success. Utilizing the knowledge derived from the measurements at Hornsea 1 combined with the introduction of our new design software, we managed to shave up 20% of the steel at West of Dutton's offshore wind farm compared to Hornsea, which was right next door. As I said before, I met Alistair after my PhD was at my PhD defense, and at that time he was working with Rambo. And I remember that evening we had a very long and inspirational talk where we both shared the ideas and visions for the industry. And we had planned to have a follow-up workshop between Ørsted and Rambo to take place in London a few months later. And at this workshop, we laid out our visions for the future, as you can see in this drawing board from that day. And our conclusions were that we needed to install monitoring equipment to ensure that we had feedback loops in place for all our as-built structures. We needed to undertake pilot tests all the way to failure, and we needed to use 3D fine element to improve our design. And finally, we needed to develop cyclic accumulation models that would account for layering and load variability. And all these we then later ended up pursuing together.
Sorry. Great. Thanks, Christian. So before I came into offshore wind, this is what I was working on. And this is actually the headquarters of the BBC in London. And you can see it's a huge hole, an 18-metre deep basement, surrounded by all these listed buildings. And underneath it, it has the Victoria line running, and alongside it, you've got the Bakerloo line. So these live railway lines surrounding this enormous hole. And the engineering involved was really fantastic, especially for a young engineer like myself. And we did some really good work. We had multiple boreholes across the site. We've done some really great advanced lab testing to get our small strain stiffnesses. We did some 2D FE modeling. You can see the cut through here. And then the 3D models, and this is 2005, took sort of 3 days to run. But we did manage to get them working, and that allowed us to look at the corner effects in these big basements. And fundamentally, this tube tunnel moved 50 mil during the construction of this site. And that was what we predicted. So doing this sort of project was both technically challenging, but we also had to bring everyone with us. And it's actually great. This was the first project where I worked with Felix Schroeder and GCG, who have also followed me into the sort of offshore wind journey that came after this one. So when my company got bought by Ramboll, I moved to Denmark. And one of the first projects I ended up on was the Walney 1 project. And here's a nice picture of it with the UK Lake District in the background. And I found a sort of complete contrast. So having been in this, whoa, there's a step there, having been in this very highly technical London world, to go into this sort of very process-led design, just using basic API curves. We had very poor site investigation, I have to say. Most of its focus was on picking peak strength values. We had a stiffness problem, but we just related stiffness to strength. Scour was apparently just 1.6 times the diameter. That's very useful. And for cyclic loading, Christel, we just multiplied by 0.72. So that was our design approach. And actually, when these projects now come up today for their lifetime extension or some sort of reassessment, I have to admit, I'm almost ashamed to admit that I worked on them. So in preparing our paper, we want to make a comparison between all the different design approaches that we've used over the years. So what we've done is we've used our software to take a 15 megawatt turbine, a typical North Sea sand and clay soil profile, and we've done a design. And if we just apply the approaches as we did at Walney 1 back in 2009, we will find that we get a power weight of 1,540 tons. So now, starting from that very basic approach, I want to talk you through the developments that we have seen over the last 20 years since that time. So later in 2009, we came on to Sheringham Shoal. Now this is an Equinor wind farm, or Statoil as it was back then, and Tor Inge was our client. And as a client, they were definitely ahead of their time. And they'd done a far more detailed site investigation. And actually, we were working on the extension to this project last year, and it was quite fun to see Andy Barwise's name on the front of the site investigation. Now, this site investigation included cyclic testing. That was pretty novel. They'd actually done some Bender element tests, and also some downhole geophysics to understand the stiffness profile. But the challenge of us as designers was, how on earth were we going to use all this information? We were typically used to just basic API approaches, and our fee, I have to say, was also based upon that. So applying techniques from the BBC, I was able to take some of my modeling skills and start to try and do some FE modeling of these monopiles. Now, unfortunately, the range of parameters I had basically meant I could make my model prove anything. I had nothing to calibrate my model to, and that's probably the biggest problem. Ultimately, we had results, as we show on this slide on the right. We saw much, much stiffer behavior from our FE modeling, but did we dare go that far when API told us things were softer? But probably the most valuable thing that came from this, and what we implemented in Sheringham Shoal, and I think for the first time, was the concept of the SY toe shear curve. And this had a great effect. You quite clearly see it from the FE modeling. And taking our standard monopile, we've now down to 1,400 tonnes, i.e. we've got a 10% saving compared with our Walney design approach. So effectively, that toe shear is 10% of our steel. The next project that was actually the first project that Christian and I worked on together was Westernmost Rough, a project off the coast of Humber in the UK, and it's dominated by low to medium dense chalk. And actually, what we're concerned is based upon our knowledge to date, we really didn't understand how the piles worked in chalk. We're particularly aware that in Thanet, for instance, the piles had just sort of sunk in under their own weight, and did they have the capacity that we needed? Now, on the Thanet project, fortunately, a test site had been identified. It was never ever used, but the St Nicholas Wade site in Kent, which has then subsequently been used for all the alpaca testing, was set up. And there we were able to do some very basic pile testing, pulling the piles horizontally. We also did a bit of vertical testing. And this work was much reported on in the Oslo conference. And to be fair, alpaca had probably since made a lot of it superfluous. But what we were able to do here was two things. First of all, we were able to understand how to do pile testing. And I actually think that the mistakes that we made in doing this pile testing went on to give the success of Pisa, Picasso, Vikingo, and all the other pile testing projects that followed. But what we're also able to do is understand some of the mechanisms that we were seeing, and the concept of the bilinear PY model we introduced. And also we were able to use some of the back analysis that we had from West of Dozen sands to inform our sand and clay stiffnesses. And ultimately, we take our standard monopile weight and apply all of these different adjustments. This gets us down to about 1,200 tonnes. And this is still prior to the establishment of the Pisa project. Now, when we were asked to give this keynote, I was asked not to talk about Pisa too much. And it's true, the Pisa project probably has been talked about rather a lot. And I think at the last ISFOG I attended, I even played Pisa bingo as to how many times Pisa was mentioned. But commercially, it does form part of this story. And here's a photo of all of the Pisa team from, well, not all of them, I'm sure there's some who are missing. And it's been lovely last night, actually, meeting so many of the people who are in this photograph. And it shows to make big steps forward like the Pisa project, you need a lot of people involved. But you also need a lot of time. And Pisa, for me, takes up a quarter of this 20-year period that we're talking about today. Now, commercially, what were we doing for that 5 years? And actually, more than half of that 5 years was spent trying to establish the project. I had to find a contractual mechanism that would allow all the different developers to collaborate. I had to try and get them all to cough up, initially 200K, we expanded it to 250K when I ran out of money. And ultimately, that took 2.5 years. When you then consider that actually the Pisa itself was a 2-year project, we spent more time preparing for it than actually doing it. Now, I think when we look at that 250K, and I look at it now and think, why on earth did it take me so long to raise that money? Our standard North Sea pile with a Pisa methodology comes down to 1,100 tonnes. So that means, assuming that you were applying our Westernmost Rough approach before Pisa, you're going to pay for yourself in 1.5 monopiles. And if you were applying the Walney approach, which many of the other developers were at the time, actually you would pay for yourself in far less than 1 monopile. And I often sort of wonder when I'm contemplating these things, why back in the Sheringham Shoal days, why did we not raise the £3 million on that project alone to do the Pisa testing? And how different the offshore wind world could have looked if that had been the case. Following Pisa, and lots of projects adopted Pisa, and I think trying to work out what's the first project is quite difficult, especially as lots of projects sort of adopted it before it was published. But one of the first that I worked on was the Careers Flak project. Now, as a byproduct of the Pisa project, which was very much targeting monotonic loading, we did do some cyclic testing. And this testing formed the start of what is now an ever-growing database of high-quality cyclic pile tests. And it's lovely as we get conferences like this that we're seeing that database become more and more public, There's still probably more private tests in there than there are public. Now, what we're able to do then is actually start to calibrate the models which we've been developing, and Christelle's talked about some of those, and to actual pile tests. And so suddenly they actually become believable. It's back to my FE problem. If you don't have anything to calibrate to, are you just shooting in the dark? And we did this at Creers Flack, and the results of applying the sort of PISA approach and the cyclic degradation models that started to come out here, we get our pile down to 1050 tons. So this brings us to the present day, and here's a photo from about a few weeks ago. This is a tour project going in off the coast of Denmark, here we have a pile which is being designed by us using as many of the latest techniques as we possibly can. Now, it has to be said that one of the things of the PISA project was it's all about matching FE to soil reaction curves. And that's because back in 2009, when we dreamt up that project, we did not have the computer power to run 3D FE across every single monopole. We do have that power today, and actually that makes it very different. This means that we can run 3D FE across every single location. We can then use those actual 3D results as opposed to the traditional curves. And then we can apply our cyclic degradation models, and these are becoming more and more complex. And as I think we sort of just heard, this is certainly an area where we'll see more development over the next few years. So this brings our pile, our standard pile, down to 1035 tons. So if we wrap up this evolution of a monopole, what we can see is how over the last 15, 20 years, we've brought the weight of our standard monopile down by 1/3. So the geotechnical designer has contributed to that 1/3. That's a huge amount of money that we've added. And when you think on top of this, we've also had higher quality site investigation, which will add lots more. And the structural engineers have also done a significant improvement over this time. We can be really proud as an industry how we've contributed to lowering the cost of energy. There's actually a similar story within the jacket or pin pile base field. Now, I think a little bit like the monopiles in that we actually started off a little bit backwards within offshore wind. And when you consider that Richard Jardine and Fiona Chow first published their CPT-based methods in the mid-90s, the first offshore wind jackets and also the substations were very much designed following very basic forms of API. Now, the Borkum West 2 project pictured here, I think, and Bruno confirmed that he thinks the same last night, is the first time that the ICP method was applied within offshore wind. This was these tripods designed by Caffey Associates. And as part of a review, the ICP approach was introduced. And by applying ICP, also applying a method to properly account for cyclic loading, the saving to the pile was in the order of 25%. And this is nicely reported by Merritt et al. In the OSIG 12 conference. Now, unfortunately, we were pretty quick to forget such lessons. And when you look at the picture on the left here, this is the westernmost rough substation a few years later. And what you can see is, even though it's a comparatively light structure, we ended up with 2 piles in each corner in order to provide capacity because of the way that the skin friction was just limited to the Syria value of 20 kPa. And as the engineer ultimately responsible for the design of this substation, I definitely, at the time, I was guilty of focusing on the monopiles at the expense of this, and possibly also that the UK OFTO regime, by which you get paid back all the money you use to build the substation, perhaps didn't encourage me to do a good design. But looking back now, we could have definitely done a better job, and I'm pretty sure we could have got it down to 1 pile per leg. This substation completely contrasts, though, with the excellent work done by Pedro Barbosa et al. At Vikinga a few years later, where for the jacket structures there, they undertook offshore pile testing, proving resistances significantly higher than could be otherwise used for design. And this is a really great example of how pile jackets should be designed. More recently, then, we moved to Taiwan. And fortunately, we've now learnt our lessons. And so in 2016, as the offshore wind industry took off in Taiwan, we became, as engineers, very concerned with the high mica contents of these soils. And something in hindsight we actually completely overstated. And especially when you look at the mica contents of the Mustang Island pile test, which set up the API PY curves, I think we probably significantly overstated it. Now, Avi has reported much about the Ørsted and NGI testing, but we also did some testing for CIP. Now, we had a site that was much closer to shore, and this allowed us to do it onshore at our substation location. And doing onshore pile testing is actually, well, it's a lot cheaper, but also allows you to investigate a lot more because you can install so many more piles, you can do more aging tests, you can do more cyclic tests. And this allowed a proper construction of cyclic interaction diagram. We really understood the aging effects, and actually bringing this all together, we were then able to save 45% of the pile length. So that's a huge amount of money saved for this project through a cost of $1.5 million US, which was the cost of this pile testing. So what this is showing us is actually we can do pile testing on a project. It can pay for itself on a project. And actually, where this pile testing has really helped has been the subsequent projects, which have then had this data for free and able to deliver some very, very efficient designs on the back of it. So in the pin pile summary, we're far better engineers now than we were 20 years ago, and we've learned a lot about how to do pile testing. And we must remember that if we are doing pin piles, we should be asking ourselves the question of why not do pile testing. It's something that can normally be afforded on a project.
Just briefly on the use of suction caissons or suction buckets. Back in the early days, there was a lot of focus on this monopod bucket, which was thought as an alternative to the monopile, but would be noiseless. And here to the left, we see a mobile met mast that I was leading the installation of while I also was in Ørsted. And we managed to safely install the foundation, but after this installation, looking at the results, we ended up concluding that we wanted to divest the concept and not use it anymore because we had some big concerns about the installation. And I think the main reason why this concept is challenged is that if you want to make it cost effective, you really need to have low DOT ratios, so the ratio between the diameter and the wall thickness of the caisson. And it can be really hard to achieve these tolerances and secure that during installation. And basically, if you have an uneven skirt and you try to suck that into the ground, you won't get to a full penetration. So there's been trials afterwards in the industry, but they have also been unsuccessful as late as a few years ago at the Chibuk offshore wind farm. And I think today there's no one looking at this concept anymore. Different experiences we've had with the suction bucket jackets. After discarding the monopod bucket, we started looking at the suction bucket jackets while I was in Ørsted, and we deployed the first prototype at Borkum Riffgrund in 2014. And that became a success, and we've later seen suction buckets being installed in Aberdeen Bay and Borkum Riffgrund, and lately we've seen that in a large-scale deployment at the Seagreen offshore wind farm, where we've seen 114 foundations being installed. So we will see more suction bucket jackets in the future, but I think still we would, as I said before, that monopiles are the preferred option for the developer, so we will see the suction bucket jackets whenever we have rock that prevents pile driving, or if there is noise restrictions that are preventing the monopiles to be used. So over the last decades, we've really been expanding around the world, and that has also led us to a lot of new geotechnical challenges. We've really seen new complex geometries that differs a lot from what we're used to up in Northern Europe. We have seen an increased focus on drilling pile runs and pile driving risks. Also, a lot of the sort of easy sites in Europe have been used, and we are left with more challenging sites, so we've got challenges, and that's led us to look at a lot of alternative installation methods, variable driving and jetting, and also We have areas where we see earthquakes and liquefaction risks, which is really driving the design, and we have a lot of new problematic soils, such as the gorgonite and carbonate sands that we need to address. So there's still a lot of work for geotechnical engineers. And we thought about what a few key messages would be looking into the future. And I think, firstly, adding complexity is not always progress. A simple, well-calibrated model that reflects observed behavior and can be explained transparently will often outperform a complex one. And we see that this unnecessary complexity can really lead to over-design and higher costs and delays. So I really encourage you try not to overcomplicate our methods. And secondly, I think we need to trust our field data a lot more. We tend to rely heavily on lab testing, especially when it's reconstituted samples and cyclic tests, but these can really mislead us sometimes and introduce project risks. So increased use of in-situ data that reflects the real conditions will support faster and more reliable designs in the future. And finally, we must learn from what we built. So systematic back analysis, we see that as really essential to continue improving and validating our design methods. And to do that, we also need an industry that is increasingly open to share data and not protect their data. And I'll leave the final words to Al.
So it can be tempting to come to conferences such as this one and hear all the technical excellence that's going on. And actually, you think that everything's rosy and the industry's fine. But offshore wind over the last few years has been facing significant headwinds. So if we look at this graph here, we've plotted up the Global Wind Energy Council prediction for what will be the number of gigawatts being installed in 2030. And what we see in our bold lines is that back in 2022, they predicted we'd be installing 38.9 gigawatts in 2030. Whereas the latest prediction that they've now produced for April 25, they've reduced this number down to 19. So you can see, yes, the industry is growing, but it's no way growing like it was predicted to 3 years ago. And what's caused that? And the same things have also impacted other energy sources. But inflation has added about 22% to the cost of wind, particularly capex, so the cost of our capital. And again, the cost of capital means that offshore wind became addicted to this sort of 0% interest environment. Now we've got interest rates more 4%, 5%. That's added about 35% to the cost of our projects. And then on top of that, this is a political game. And we've got a lot of political uncertainty in the world. And the number of elections that we had in the last year led to a lot of auctions getting delayed. And then finally, and probably my biggest headache today, is our friend Trump. And I really, there's a brilliant BBC podcast called Trumped on BBC Sounds. And this is all about how he didn't succeed in getting rid of the Aberdeen offshore wind farm. And since then, he's had this personal grudge against offshore wind, which is really, really difficult to shake off. Now, it's tempting to think that's just from the US, and we've seen a number of developers withdraw from the US. But what we have to realize now is actually capital is tied up in those US projects. So if you've got a US project under construction today, and you want to sell that project down, which would be the conventional business model in order to free up that cash to invest in future projects, currently you've got a stranded asset, because until you finish construction, you're not going to be able to sell that. And that's leading to knock-on effects around the world in other areas where offshore wind farms are also being built. But what we should say is that actually we're still seeing growth in our industry. We can still see we've got a 20% CAGR, very similar to what was predicted 3 years ago. And actually, if we look at the costs that have been added to all of the other four sources of energy, and this is data from the UK Office of Budget Responsibility, so the sort of UK independent auditor, we can see that even with all of these costs added on since the invasion of Ukraine, offshore wind is still a very, very competitive source of electricity. I think probably what has changed, though, is it's no longer about we must be green. This is now about energy security. All global economies are seeing their economy electrify as we use more and more electric cars, as we move more data centers, and demand for electricity is increasing worldwide. So this means offshore wind is part of the story, and we've got to produce these new power stations to help deliver the global electric economy. So, as a geotechnical designer, you've seen we can have significant influence on this. And that 30% or the 45% that I mentioned in Taiwan, that's a difference between a project working and a project not working. But unfortunately, we still don't always get things right. And this was a design that came across our desks while we were writing this paper. And we've got a wind farm that's almost identical to a one which we've designed. The site that we've designed is 1795 tons, the maximum weight of the monopile. Whereas this is the adjacent site designed by someone else, apparently still using all the PISA methods, still applying all the best latest cyclic models, comes up with a monopile weight of 2074 tons. So there's still something that we're not doing right within this room if we're still not turning out the best designs. And these 15% could be the difference between this project going ahead and this project getting cancelled. So, our final thoughts. We're not designing things the way we were 20 years ago, and we should be very open about that and not ashamed of the mistakes we are making. And tomorrow, we won't be designing things the way we are today. What does that make it? It makes it a really exciting industry for us to be in, and I really look forward to hearing all of the work that's been done in this room and understanding where we're going to go in the future. Thank you very much.